Okay. So, welcome to another session. So after the Python primer, we're going to get into HTMD. So now that you have an overview of Python. So this already assumes that you have downloaded and installed HTMD, which in the machines that you already have available already have HTMD. Otherwise, you'd have to install HTMD, which you just go to the page and follow the instructions, which I think they are pretty clear. So here in this presentation, we'll focus on the molecule class, which is one of HTMD classes, and the features of the molecule class will serve as a good introduction for more complex features of HTMD. Okay. So that link over there, that thing over there is a link, so you can actually click it. So let's get familiar with the molecule class. So the objects in this class are meant to store the structural information on molecules. Okay. And despite its name, the molecule object does not only contain a single molecule. So here we follow a little bit like BMD, the definition of molecule, which basically it contains a whole system, including water, ions, protein, ligands, lipids, etc. So think of it as a container of structural information. It's actually very flexible and very useful. Okay. Actually, I think that you cannot do anything else. Sorry, got to do this again. So, okay. So first of all, as we see before, we need first to import HTMD. So that any class and function defined by the HTMD is available in workspace. So we are doing it through this way, and I think I suggest you to use it. So here, so we do from HTMD, we import star. Import star is importing everything, and it's not everything. It's everything that is defined in a special file that we define for everyone. But basically, it's the general stuff. We put it in there. Sometimes experimental stuff is not in there. But basically, when you do this, you import everything that you may need. And another aspect of this is, as I told you before, you get rid of HTMD namespace. So every function don't need to start HTMD dot with this type. Yes.
Are you sure that this doesn't overwrite somewhere?
Yeah, that can. Well, we have fairly non-general names. We try to have non-general names, so I think they won't override. If they override, is by sheer and luck, basically, bad luck. So other than that, you can import HTMD and then use the namespace in which, well, as you may say, it's safer. So, but sometimes it's boring to do HTMD function. So, okay. So let's actually do it. So everything else on the notebook works. So basically, this is a welcome message. So as soon as you import it, you have this nice welcome message where you see which version you're at. Actually, you all will also be on 1.5.4. Some information about the paper that actually talks about HTMD. And when you're starting this for the first time, it also calls you to have a license, but that's another thing. It's not important for you. So reading files with the molecule class. So the molecule class provides file readers for various of structured formats: PDB, parent top, ESF, GRO, MOL2, Maestro files, much more. It also reads a lot of trajectory files, mainly XCC, but also other trajectory files through also MDTrad, which is another package that we use. So the method for reading files is actually molecule. So molecule is the class, okay? Molecule is a class that is imported when you import HTMD, okay? From HTMD import start, molecule is imported. And then this class, a class is basically a conjunction of functions and properties, okay? And these functions, for example, which are actually formally called methods of a class. For example, molecule class has a read method. You can actually click on this link and go to the documentation where this method is in HTMD.org. So, but more than just using this method, you can actually call the class because the constructor actually automatically calls this method, okay? The molecule.read, as soon as you put here something. So basically this is the most common, the most simplest command that you can do on HTMD. So you just call, create an object, a molecule object, using this code over here. Here, basically, if you can either do it something like this with a 4-letter digit, which basically means that it goes fetch it from the PDB database, or you can give your own. So also with as a string, a path to your own PDB or to whatever file that you want to read. Okay. So here, if you run this is ACEMD scene. It gives just some information because there's already a local copy of 3PTB, which is something that we already use. So instead of searching for the database, it already draws that one, so it's fine. So this is completed, and basically this loads everything into a molecule object, which we call mol. Okay, so this mol now is formally this is mol is an instance of the molecule class. Okay. Some more extra information about structural information is that, so PDB files, for example, which is probably one of the most common things that people work with, contain atom information and coordinates, but they also can have other information such as bonding, but also the PSF files have atom coordinations, atom coordinates. You can read also the bonding information, okay? So you can actually do something like, for example, if you want to read a trajectory file, but first you want to have some bonding information, you can do something like this, which is just first read the PSF file to a mol object, and then you read the trajectory into this file. And basically, it's going to have, all the trajectory is going to have the correct bond information that's already provided in the PSF. Okay, so this is also a common thing to do. If you want to write files that you read, you can also do it through the write method. Okay, so here we already have an instance of mol and not a generic thing. So this is already mol with already the information. Just use the method write and write whatever mol has. Okay, using its write method as a DCD file, for example, or write a PRM top from whatever information it says. Okay. So when you have the molecule instance, okay, you can actually do this print molecule. It's going to get a little bit, well, you can actually see everything when you're not on presentation mode, but it gives already a rough idea of what you get. So you get the information of what you have in the mol instance, okay? So this is the kind of fields that are defined. Some of them are already known. Charge, chain, beta factor, coordinates, the elements. So many information that is read from the PDB file is already here. We have also other kind of information like angles and bonds and stuff like that. So, but this is basically just, we never use this. This is just for you, just as a checking, I guess, of the information that we have inside this molecule. So you have the number of atoms, the number of frames, so you can have more, as it was obvious, since you can load the trajectory in a molecule class, you can have more than one frame, as you can have multiple frames in the entire trajectory, okay? So, here are some of the properties and the methods that are available in the molecule class. Okay, you have a number of properties which are data associated to the molecule. Normally, it's the coordinates, everything that you have the structural information. The data are properties. Okay, and then you have methods. So these are the two types of things that you can have in classes. And methods basically are well, the methods of the molecule object are operations that you can perform on molecules. Okay. So here, types of properties: the record, serial name, res name, chain, as I talked to you before, coordinates, box, representation, something that I'll talk about later also. Then you have methods like read, write, get, set, atom select, copy, molecules, filter molecules, append, insert, view, move. So you have a lot of many functions that are available, and I think that this presentation will cover them all today. The ones that are available. Okay, so properties. They can be accessed either directly, so you have molecule. If you do molecule.serial, it actually outputs the serial of the molecule. Okay? You can actually try it. Okay, it's an array basically. It basically means that you have an array from 1 to 1702. Okay. Again, NumPy arrays, okay? But you also can use the get method, okay? You can use dot, so there is a property, okay? You're getting it directly. And here it's another way of doing it, which is small.get. This is a method, and we want to get the serial, okay? This property. Basically the same thing, okay? Of course, you say, so what's the use of this? The thing is that get is more powerful, and you'll see it later, because you can use selections and stuff like that to trim down whatever you want, and while mod.serial will always give you everything, okay? Well, not always, you can also select things, but... Similarly, you can also modify directly using mod.serial, or you can use molecule.set, so the set method of molecule, to modify directly this thing. So after you load the molecule, then you want to do some modifications, and you can use these sets. You can get this information and set this information however you want. So these are normally called the getter-setter methods in object-oriented programming. So of the class, you have the getter and setter things to have get and setter properties, okay? So in the following sections, we'll see a little bit more of this in real world applications. So here we have an application. So check the residue IDs of cysteines in the molecule, okay? So in order to get the residue IDs of molecule, we can do this kind of command. So let's see here. Small.get, so the method, I want to get what? The res IDs of what? A selection which is called res name 6, okay? So there, what we expect to have as an output is of this selection is going to match everything in the molecule, okay? That selection res name 6 is going to match everything in the molecule, and then it outputs the res ID corresponding to that particular selection, okay? So basically, we get an array of res IDs. We can see immediately which are the residues that are cysteines, okay? And a note here is that residues IDs are outputted multiple times. This is due to the fact that this is returned for each matched atom, okay? Since there are 6 atoms of cysteine, it gets outputted 6 times, okay? For each one of them. So, for example, you can get the names of 6 atoms of cysteine. Residue 58 can be checked with this command. So you just, for example, you're interested in residue 58, and now you want to check, for example, the names of the residue. Okay. So use another selection, res name 6 and res ID 58. So this is actually taken from this kind of selection is taken from the VMD. So you go on our documentation, you can actually see it, how these things are performed. Okay, I can actually show you that. So let's go there. So if you go on HTMD, okay, you can go here on the documentation. It's also interesting for you. So we have tutorials available, we have user documentation, okay? You go here on the molecule, you can learn more about the class, okay? And you can actually see that the atom selection is identical, it is based on VMD's atom selection language. You can actually link to it, okay? Or you can see some documentation that we have here prepared, okay, of how it works. So some examples of how you can select stuff, okay? So you can actually go back here on this documentation and check some of the things that some of the code of the syntax of how to do selections. Okay. Okay. So, for example, to obtain one res ID per residue, one can either further restriction the selection to C alpha, so carbon alpha atoms. So basically, we add here name C alpha, Ca, which is carbon alpha, and res name cysteine, and get the res IDs, and then now you get one for each. Okay. Or we can take advantage of Python and use the numpy.unique function, which removes repeated entries. So these are two ways of doing it. Okay, doing the same thing with the same output. Okay, so remember here, a note here is that numpy is already imported when HTMD is imported. Okay, as the NP, so which is also useful. We can also, for example, retrieve coordinates of atoms. So we can also do another get. Now, as you may see, you get coordinates of this res name cysteine and res ID 58 and MCA. So this basically gets the coordinates of carbon alpha of residue 58, which is a cysteine. Because res IDs are not unique. You can have res IDs, for example, waters that can have res ID 58 also. Okay, so. And this you get an array of it, okay? So take a note a little bit also on the precision, that it goes to the third one, and then you lose precision of the third one, okay? After the third. So the precision of the PDB is actually 10. So if you have more than one atom, okay, then it returns a n times 3 matrix, okay? So for example, if you want the entire, it will output a matrix with every entry, okay, of each atom. Other things that we can do. So now, for example, we can get the chains present in a molecule, okay, with molget chain, and then since we'll have one for each atom, we'll use again numpy to trim it down to just the unique chains that we have. And this is that you just have chain A, okay? Which means that every atom that we have is assigned to chain A. If there was something else, for example, even if there was undefined things, it will show then, for example, comma and then an empty string, which would be, for example, atoms that don't have a chain identifier, okay? The same can be done for segments. Okay, and we have two segments here, 0 and 1. And segments are actually very important for building, which Tony will talk next on the next presentation. It's important because we use segment IDs, not only we, but some software use segment IDs to define chemical molecules, so things that are molecules that are separated in their system. Okay, and so it's important to define it. So we've seen a lot of gets, getting a lot of properties. Now you can also going to see how to set some properties. So As I said before, the .set method, so the set method of molecule can be used to change, name, rename specific fields of the molecule or a selection of the molecule. So here we have an example of creating segment ID called P for all protein atoms. So here protein is a selection type that actually withdraws again, you can check the documentation from the VMD language. So this is something that VMD commands, so to speak, or syntax to understand everything that is a protein inside the molecule. So everything that is a protein, I want to change this property, which is segID, to this particular string. Okay. So we saw before that we had two segments, 0 and 1. And now we're going to have, well, we'll see what we get, because after this I'm going to get the segID of the protein to see what was done. Okay, and we'll see that. Now we just have the P segment. Okay, so first we set it, then we just get it. But this is just to check if what we did was what we wanted. But normally we don't do a get after a set. We just do a set and that's it, because we know what it's doing. If we know what we are doing, of course. And another common, for example, this is a very common thing, which is renaming the histidine residues. Normally you just want to change protonations and stuff like that, and then you want to rename them. So you go on the same approach, okay? So I want to go to every res name is, so every atom that is with a res name histidine is, and then I want to change the res name, which is the same thing, but it doesn't matter, because it only changes after it already matches. So every res name to a HSN. Okay. And then we just get the serial of everything that's called HSN. Okay. I have a lot of histidines on this protein. Okay. More things. So, count the number of waters in a molecule. So we can actually get the indices that will recognize as water. Again, water here is another command to recognize automatically water. Okay, another magic word. So you get the serials of all waters. Okay. So in this case, the hydrogens of water are not present. So I already taken this into consideration when doing this, because if there were hydrogens, the output would be this, okay? Otherwise, we would use the NP function or some other thing as we did, for example, selecting the oxygen of the water or something like that, okay? The number of the waters shouldn't be out of, well, it shouldn't be out of the scope. Anyway, you can do it like this also. So this is a way, I can exit the Python, the presentation, because this is, and I can show you here. So here, so basically here we are doing the same thing that we did above. Okay, so we have an array with all of those numbers, and then we are using this function that just counts, which is len, which counts the number of elements of an array, and then we have the automatically the number of water molecules that we have on the system. Okay. Or actually on our molecule object. Okay, so another way of doing it is using atom select. So So this, when we do atom select, is another method of molecule, and actually it can be used and returns a boolean of values. So what that actually returns, I'm going to show you so it's easier for you to understand.
Control minus, well, control minus makes it smaller representation.
Oh, thanks.
Find the minus.
Yeah. Okay. Thanks. So here you don't see much, but basically what it already gives you an idea. So atom select, what it gives here is that it goes to all atoms and see which match and which don't match. So for the indexes that don't match, it gives you a false, and for indexes that match, it gives you a true. So basically, we'll have the array with the length of the number of atoms that you have, but then for water, when this is true, for a given, it goes along every, so it just returns an array with that size, where each index is even true or false if the corresponding index is a water or not in the molecule, okay? So basically it's an array which has 1,702 items, and then of those 62 are trues and all the others are falses, okay? And they are in the exact order that they appear in the molecule, okay? And using this thing, we can actually use another function which is called sum, which basically checks the truths as ones and the falses as 0, and there actually is another way of getting the total number of waters. So, but basically it's just to showcase another way of doing the same thing, but also using other tools that may be useful for other purposes than the previous tools can't be used. Basically here. So as you expect, the waters are in the end. So when the array is too large, it shows the first element, and it's ... and then shows the last element when it's too large for it to show. Okay? And basically the first elements are not water because they're more likely protein, and then in the end we have waters, okay, so to show. So this is the exact order that is read from the PDB, which is normal. Okay? So let's go to a fun part. Well, at least I like it, which is representations visualization. So we have this molecule, but now we also have other things that you can do other than this handling and setting the properties and getting the properties and see what inside, which is actually visualized. When you have a molecule, you actually want to visualize it, right? So molecule objects in HTMD can be visualized with either VMD or NGL, which is an WebGL JavaScript molecule viewer that is integrated, okay, in HTMD and in the notebook, okay. So as by default, VMD is used as a view. So if you don't specify anything and you do a view command that I'm going to show you afterwards, it's going to use VMD if you have it installed. Otherwise, it will fail because it will call and try to see if in your path you have VMD installed. Okay. So if you cannot call VMD on your terminal, it will probably not work. Okay. But if you don't have VMD or you don't want to use it, you can actually use NGL. And for that, you just do this command, which is htmd.config, and then you set the viewer to MGL, okay? Which is actually what we're going to do here to show you in the notebook the visualization, okay? So we set it up, it's okay, and now we can on the fly visualize this molecule and interact with it, okay? So again, we are going to reload the molecule, and then we are going to use the .view method. Okay, the .view method is what we use for visualization, for visualizing the molecule. Okay. I almost got scared because this was not working properly recently, but it's again working. So you can actually see the molecule, okay? Let's see if this works. Well, I guess I cannot zoom with this mouse. So with the wheel, if you have a mouse, with the wheel function, you can zoom in and zoom out. You can right-click on it and rotate it, and you can also, this one, which is left-click, which is move it around, okay? So you can see that the protein is shown as cartoon, okay? cartoon representation, then the waters are in red spheres, and then you have there a small ligand, which is benzamidine, okay, which is shown in kind of a ball and stick configuration, okay. So this is quite nice because you can actually inside the notebook, you can start to get and set these properties and change stuff, handle around the molecule, immediately view your output. You're going to see some examples of it, okay? Another powerful thing that has been recent is that this interface actually now has a GUI. So actually it makes it more similar to the power of VMD, which you can actually do as VMD, go to representations, and then in this presenting mode is not working so well, but in the normal notebook when it's not presented mode, it's nice. You can actually refresh, center, hide, remove, and representations, add new representations. So actually it's a little bit more interactive. So this is a new feature that Stefan implemented. Actually, no. Stefan implemented a way of HTMD having this. But it's true.
An option too.
An option. Yes. Yes. You wanted to say something? Yeah. I thought it's implemented. We're just reusing it. We're not we're not taking credit from him. We just didn't have this option, so we decided an option to have it. So actually, Stefan had some work on it, and well, I don't think it's nice because I mean, you can always use VMD, and everyone. I mean, everyone uses VMD, and you can actually use it, but actually, it's a nice feature. Okay, let's move on. So you can set it up with this GUI equals. Well, by default, it's false, but you can set it up to equals 2. Okay, so now 2 ways of visualizing things. Okay. You can either use the view method and then do on the fly set up things that you want to visualize, like for example the selection that you want. For example, protein, I want it in this style and then this color, and it will give you right away this representation that you're choosing. Okay. And if you want more than one, you can set this command, which is called hold true, and it waits for another view command, okay? So it gives this representation on hold, and it puts, they put another representation, which is, for example, resonant band, which is benzamidine, in licorice, and with this color, okay? So this is the transient. So nothing is saved on the molecule, just want to set up something. So we just want to see the molecule object with these kind of arguments that we are passing, okay? Representation arguments, so to speak. Okay. So you can see here that the cartoon is now how we define. So it's a cartoon representation with the coloring going along the ID, I guess. And the benzamidine is colored in red in licorice, okay? So, but there's another way to do representations, which is defining it on the reps property, which is actually another class, but doesn't matter here, the reps of molecule, okay? So molecule has a reps property, which can store representations. So here we can go on the representations and remove them. So since reps is another class, it also has its own methods, okay? So it's a class within a class. This is more in detail, okay? So we can actually go to the representations of molecule, which are none by default, yes, and then remove them if you have something already. Then you can add new representations. For example, we're going to do exactly the same thing that we did on the previous slide, but using this kind of explicit way, where we set a given representation, the same thing that we did on the first one, and it's added to the list of representations. And we can add another one, okay? And actually you can list it, the representations that are available, and this means that every time that you do now a mol.view of this mol, it goes on the representations that it already has, and it's going to use those. Okay, so if you have a favorite representation of something that you want, you can actually define it once and then use it all along throughout the rest of the notebook. Okay, instead of always calling with the same functions. Okay, the same arguments. So basically, this is the same representation as we've seen before, okay? And here it's the output of the print.mol.res. So we have representation 0, which with these characteristics, and representation 1 with these characteristics, which is the one that we defined. So then, if in the future, if we do again another mol view, it will always take these characteristics, okay? These representations. And we can use more interesting things. So here, what I'm going to do is to remove the previous representation, okay? That is stored, and now I'm doing one on the fly, the transients, okay? One, which is basically using some maths here, okay? So here, just you can see here what's happening with basically you're just showing, you can see it from the code, that you're just showing everything which the x is the x coordinate, okay, of the molecule. It's basically we're showing everything that is outside of from 3 to -3, okay? So we're taking a 6 inches slab here, which is not showing, and we're showing everything outside of it. Just an example of things that you can do actually with the representations also. Okay? 6 times.
Angstrom, not inches.
Yes. Yeah. Inches it will be very different. So another important thing is the copy method. So as soon as you start, for example, you start to handle around molecules, you have this molecule object, and now you don't want to mess with it, you want to save it, and now you want to do another copy of it. So you can just do mol.copy, which just creates a new, it just returns a copy of the molecule, and you can save it in a new object. In this case, we call it new mol. Okay. And then with this new mol, for example, we can move it around, do other stuff. For example, here I'm just doing it. What I'm doing here is creating a new mol, and then I'm writing to a ligand.pdb file the resonance band and no nitrogen. So basically, we are going to take the benzamidine that's inside this PDB, and we're writing to the ligand.pdb, okay, file, just writing there. And actually, no H is no hydrogens, okay? So we're not taking any hydrogen, which I didn't write. Okay, most of these commands don't have outputs, clear outputs, so sometimes if you want to check it, you can print stuff, you can visualize stuff. So, another method of the molecule class, which is filter. So, filter is basically you choose a selection that you want, and then it basically performs an operation on the molecule where it gets rid of everything that it's not what you've chosen, okay? So it cleans all the atoms that are there except for the selection that you chose. For example, here on this selection, we're choosing everything that's a protein and chain A. So everything that is the chain A of the protein, okay? So here we filter it, we filter everything, and if you can see here, there are no longer water molecules or the benzamidine, okay? This is still the molecule, okay? So the benzamidine was created in a new molecule, okay? And so print it to a file. But now this was again in the molecule, the original one. We just went through it, and this is a definitive change, okay? So we just strip it out of the in this case of water and benzamidine, and also a calcium atom that's also there, okay? Yeah, okay. It also gives you some information of how many atoms are removed and how many atoms are remaining in the protein, okay. So now this is just an example, a very simple example of things that we can do moving around molecules, moving molecules around, modifying them, and the bending and stuff like that. That, for example, the ligand that we have on a PDB file, imagine that we took it from the protein, okay, but imagine that you had a ligand, okay, you upload it to a molecule and call it ligand. This is a new object that has this ligand file. And then the cleaned molecule that you have, the clean protein with no other stuff, you just use the append method, which is a method to join two molecules. And basically what it says is that you want to append ligand to the ligand object molecule to the mol one, okay? And then you can visualize it. Is this clear? So now you can see here that you have the ligand back because in this new molecule, so you took the stripped down protein, we added the ligand, and now we have the protein in the ligand, no longer waters or other stuff that may be there, that may have been there, okay?
Close the viewer.
Yeah. So you can also actually this should have been into slides. Okay. You can also do use another method which is called insert. So in append, what it does, it goes to the end of the molecule. It just appends the new molecule. So the ligand is going to be in the end of the other molecule. In insert, you can actually put it on a given index. Okay. So here I create a new molecule out of nothing, so I don't upload it. You can also do that. You can create an empty molecule, then use the empty method of molecule, and create a given number of atoms that have empty properties, though they are empty basically. But then you can fill it up with the information that you want. Imagine that you have specific information that you want to put there. You can actually use it. And then you can actually insert it at the given position of the new ligand. So for example here, remember that the ligand was created here, and we just do a copy of it, and then we insert on the new ligand and this atom. So at this previous ligand, we create a copy, and now we insert this atom on position 0, okay? But then you can insert it anywhere in the molecule that you want. And then you can also visualize it. This should be a different thing, and I'm not sure that it's going to work here. We can do this. Okay, so it's the ligand, and then this is something random. Okay, it's not much use for it. It's just something to show the feature. Okay, but you can actually add an atom, anything. You can actually add. Also insert a protein. Imagine that, for example, you had protein, waters, and you wanted to insert lipids, but you want the lipids between the waters and the protein and not in the end. I mean, there are many reasons why you can do that. You want to do that, but it really depends on what you want to do. So you can also play around with coordinates. So this is one of the things that many people want to do is when you get some coordinates, maybe you want to move it around in space or something like that, you can actually do it. So here is some basic commands that you can use. So we can actually get the coordinates, okay, which is an array. So if you do this, mol.get coords will get every coordinate of the molecule, and it's basically an array, okay? And then you can use the mean function of NumPy and actually see what is the mean value of this array. So basically, it goes to dimension 0, so it goes through every atom, which is the 0 dimension, okay? and it's just going to do the mean of every coordinate: x coordinate, y coordinate, and the z coordinate. Okay, and it's going to start it in C. So basically, what does this mean? Just going to take the coordinates, make the mean, and put it to C, which means that C will be just the geometrical center of the molecule. Okay. Well, it's not. And then why is this maybe useful? For example, you may want to center your molecule on 0, 0, 0, for example, and you can use the move by command, which takes this argument, which actually we're going to pass it minus C, which means that we're going to subtract every to every coordinate in the molecule. We're going to subtract this vector, okay, which is the mean, which means that the mean will be on 0, 0, 0 if we move every atom to by this vector. Okay, is this clear for everyone? And then if we get again the mean, now we'll see, well, due to the precision, it's not 0, but it's 0 basically. Okay. Other things that we can do that are actually also useful is to rotate. So sometimes when you're trying to build given systems, you want to do some rotations to put the ligand around in space, or rotate the ligand, or something like this. So we have this rotate function that we have for in the molecule class also, rotate method. So we're going just to show an example. So for example, you can load again the molecule and filter it just to the resonant band. So you see, well, now you understand what this means, right? Just loading the molecule through PTB, and now you're going to filter just the band residue, which is the benzamidine, and now you're going to visualize it, which means that we're going to only visualize the ligand. Okay? And you can see its orientation. It's basically it's going to show like this. Okay? Now, if you use these commands, which basically using the same thing, getting the coordinates, okay, the mean, and get the ligand center, okay, basically the same thing. And then we just define, there's a function on HTMD to define a uniform random rotation that you may want. Okay, you can define still a rotation that you want, specific one, or you can use this function to put a random rotation if you don't want to, you want it to be random for some reason. Imagine that you want to start many simulations and with the ligand in many different orientations. Okay, you can use this function and start random orientations of the ligand. Okay, and then you use the rotate by function too. And you take this basically this end, and you can see in the health function of rotate by, it's a matrix of rotation. You can take that and the center as the ligand center, and you rotate it over its center. Okay, it uses this matrix of rotation and the center. Okay, to see to relation to which relation it and to which point it rotates to. Okay, so or axis, you know, so. Okay, so here we're going to do the rotation and do again ligand view, and as you can see, it's already in a different orientation from the one that we had before. Okay. Well, this one is an example of rotation around an axis. Okay. Where I'm not going to visualize it, but basically it's, instead of you can do many things, because you can rotate the ligand within itself, within its center. Then you can use, for example, a protein and put the ligand outside and rotate the ligand around the protein. So there are many functions that you can actually use depending on the rotation matrix that you use and the center that you choose. Okay. So, working with trajectories. As I said before, you can load a trajectory. Okay, so loading a PSF so that you have bonding information, then going to read an XTC and then visualizing it. I talked about it before. Now you're going to see it. Okay, Takes a while because it's a trajectory, okay? It's not as fast as, for example, loading a single molecule. I don't know how fast you use on these machines. Okay, it's not that bad. So you actually have this trajectory of the protein. You can see the protein inside. Okay, you can actually play it. I don't know how well this is going to perform. The resolution is not very good, but that's it, the projector. Okay. So you can actually visualize the trajectory. Okay.
How do you get the widget to be full screen?
Double click, or I think that you can also click on here, on this left corner, I think. No, I think it's just. Well, you can pause it. Yeah, it wasn't working so well yesterday. It took some time to pause, I don't know why. So, some stuff that you can do. So, you can also have this property which is called number of frames, so you can actually output the number of frames. I don't know if it's waiting for it to stop, is it? I don't know why this doesn't stop.
Close to the
Yeah, yesterday I didn't know why it wasn't happening.
But probably have to stop the can.
Yeah.
Interrupt.
If it still continues, you have to
Stop the camera.
No, but the thing is that if it's recurrent, you have to see what's going on.
I've never seen it before.
I seen it yesterday.
Well, it's not from us, it's probably from NGL.
Yeah, that's why.
We can report the issue. Oh, the restart just interrupted. No, it's still running.
It is?
Yep. Is it connected through Wi-Fi? Are you connected through Wi-Fi? Well, I lost your connection here, so that might be the reason.
No, actually it's Ethernet connection.
Okay, it's still not interrupted. Press the stop button up there. Stop. Again. Try to restart it maybe, I don't know.
Yeah.
Okay. Yeah, it's
I
need to import HTMD again.
I need to do. I don't know what.
Yeah.
So actually, you can also go through Python Notebook. It has lots of functionalities of how to do stuff. Go through these menus, okay? Interact with it. So the things that we are trying to do. So if things are stuck, we're just trying to kill the kernel that is running the Python code. So I don't think that it's ran. Let's see. Let's need to do it. I'm going to comment everywhere. Okay. Now this I don't. Okay, so we are here, and now, so going back, so we can actually see the number of frames. Sorry about this interruption. That Voltrise has, it has 100 frames, okay? So some examples of some other functions that you can use, which are drop frames. So you can actually drop frames by saying it you want to keep some frames, or drop frames by saying that you want to drop a given some list of frames, okay? Both of them take this, I think. So here we just do a copy of Montrage, call it frame 1, and then we've used the drop frames method using keep equals to 0. It means that you're just going to keep frame 0, okay? And you use on the frames, and you see that we only have 1. And on the other example, we want the last 10 frames, so we just use the drop 10 frames, create a new object, use drop frames again, and now we use drop, and we use again the A range from NP, just dropping things from the last 10, which is just 19 to 100, okay? And then we do them frames, and that's 90 frames, okay? Some biochemistry also of HTMD molecules. So we can print the protein sequence of a molecule, okay? Use dot sequence method, okay? And you can also create mutant proteins by mutating residues. For that, we have a function called methods of mutate residue, okay? So we can create a mutant molecule, okay? And we can see which res name is residue 158, for example. You can mutate it to arginine and then also get it again just to see how it changed, okay? So basically it was a leucine before, and then it's an arginine. The way that we do mutate is that we get rid of all the side chain and change the res names to do a mutation of the res names. Then most of the building process, it will be automatic. The building process it will be automatically regenerated from the building scripts, okay? Some quick and easy way to mutate a res. How much time we have left? 10 minutes. Okay. So let's go through this exercise. I think, yes. So there's this exercise that we're going to go through. Okay. So find residues in contact with the ligand. Okay. So first of all, we load the clean molecule again. Okay. 3PTB again. So benzamidine trypsin. It's the one that we've been seeing till now. So now we are going to identify the residues that are in contact with benzamidine ligand, okay? And so for that, we're going to again to exploit the fact that there is only one C-alpha per atom. Another way of doing it is again the NumPy unique, but we're using this command, which is same residue as protein within 4 of res name Ben. Again, this is a VMD language for selections. Basically, just going to select everything that is the same. So everything that is a protein within 4 angstroms of res name benzamidine, it's cut here due to the presentation. And we're taking everything that's the same residue, okay? And then we're going to output the res ID. So this will give us every residue that is within 4 angstroms, which any part of it is within 4 angstroms of benzamidine, okay? And then we output the res ID. Okay, so all of these residues are within 4 angstroms of benzamidine. So another exercise that you can have is to find duplicate residues. So again, let's load a clean molecule, and let's try to find the duplicate residues. So we have a few minutes. We're going to go through this quickly. So we can do it this way. So we can either identify duplicate residues by a PDB field which is called insertion, but sometimes this field is not defined. So, but this is a way of doing it. Okay, so we can actually do molget to see which atoms, which residues. So which atoms have the insertion field, okay, and then we get the res ID of them, and then the unique just to mean that these three atoms is where there is some duplicate residues, okay. Another way, and with a prettier print, okay, is to do also this one, okay. So it's equivalent, okay? We just create a new molecule, then we filter to the insertion and MC alpha, then we get the res ID of this new object that is filtered, okay? Also we get its res name, so we get res ID and res name, and then this is just something to make it prettier, so I have these two lists, and this thing just concatenates the two lists, and we can output one by the other, okay? Two lists. This is going to be a list of the res IDs, which is these ones. This is going to be a list of the names, and it just goes pair by each pair of them. Okay, just a prettier print. If we don't want to rely on the insertion, we can try to do some other process to list the gaps between residues. Okay. So this is more general than just finding duplicate residues, and it's relying on res IDs, okay? So it's giving you the same output, but I'm going to go step by step. So again, we create a duplicate, okay? A new copy. Then we filter it by C alphas and protein, okay? And then we get the res ID. So basically, this is going to have a list of all the res IDs, okay? And then you return that list to RID. And then we use again NumPy on that list. That's basically is going to compare the index with the actual number that's there, okay? And through that, you can actually see you can get an output which is the count, the name of, so you can get, when you have it duplicate, we'll have a count above 1, okay? You can actually, when you want to check this, I think there's another way. No, I thought this was a complete example. Because, let me, so, you can actually go here and print the entire NRID, okay? Okay, actually that's not what I wanted. What I wanted is the count. Okay, so when the residues are duplicated through this function that we're using right here, okay, when they are duplicate, we'll have a 2 instead of a 1, and then this is just those who are greater than 1. If there were gaps, there will also be a change here, okay? There were gaps in the protein. You can actually use this thing for both of things, even though that here we just detect duplicate residues. So, which is basically what we're going to find here next, okay? Actually, the one that we did before didn't identify gaps, and this one is the version that identifies gaps. That's the thing. So here we exploit the diff function, which just computes the deltas between the array elements, okay? So here it's more or less explained. 0 means duplicate residues, in this case, and greater than 1 means segments of protein missing, okay? Actually, this is the one that I was thinking about and not the other one. So what does this mean? It just means that this diff is going through all the residues, all the atoms that are available from this RID. Actually, it's the one that we defined before. It's going to see the difference between the actual res ID index and the index that it has, the given array has. Okay, and if it's the same, it's going to be so a duplicate residue. So because there's no difference, you move along the array, but there's no difference. And if there's a jump, it's going to show you which actually the size of the jump. Which is a jump of 3, okay, or a jump of 2, or a jump of 5, okay, which means that there's where are the gaps through this diff function, okay?
So a couple of minutes, okay?
Okay. Actually, this is the last cycle left. And you can then explore this a little bit more because you have access to this, okay? So you can actually print the res IDs, okay? Again. To see where the deltas. So here it's a way of doing it. So where the deltas are different from 1, okay? And actually this one not only outputs the holds but also the duplicate residues, okay? Because it's different from 1. If you just wanted the gaps, you just put it greater than 1, okay? Well, this is just a printed output of the same thing. So basically, it shows where are the gaps, okay? From 34, residue 34 ASN, followed by 37 serine, and so on and so forth, okay? I think it's the last, yes. So this was already an overview of the not only HTMD, of also the molecule class. Do you want to say something, Jenny? Well, after this, it will only be we're going to start to build further and further more functions and more things that we're going to show. So this is just the initial set of functions that you can use to start with. Okay, just load the structural information, move it around, handle it, change things, get information, visualize it, and stuff like that. And this is very useful as a way of moving on for the building, the simulating, and the analysis. Okay.
Question? Do you have symmetry operators built in sometimes in terms of when you download DNA or homodimeric structure from Tetra into a ion channel, you just deposit one subunit in the PDB. So if you download the PDB code directly, you will just get one chain.
I know. We are actually we had this as a project, and it's something that we're also for the crystal structure. So that's important to define which are the symmetry mates. So this is just from the symmetry unit define which are the other possible. So in the crystal structure, so I'm not so familiar with DNA, but I know that's the case also.
For ion channels, for example.
Exactly. Yeah. The same thing. So. And actually, we had the project like this, and we'd like to also implement that. Also, because the thing that we're more so we are going to talk. I'm going to talk a little bit what was our initial interest. Our initial interest was because of packing, crystal packing. So, and we're actually Jenny is actually very interested in that because of some study. I think that they've never faced any, or we never faced any case of having a subunit and then having to multiply it. So, but yes, definitely it's a function that we need, and that we're probably going to have it in the near future.
We actually have it, but we never tested it.
Oh.
So
yeah, this is the most. Yes.
So when you mutate a residue to another residue, you say either more atoms or less atoms.
No, always less. So the way that we do it is like this: we go to any residue that you want to mutate, it's just going to get rid entirely of the side chain. It's going to just keep the backbone, and it's going to change those those res names to the ones that you want. Basically, this is what mutate residue is doing. It's actually a very simple function. So then you rely on the delete or BSFM. So the building engines to actually reconstruct the rest of the
So
residue.
you're really just mutating the sequence.
Exactly.
In a sense.
In a sense, you're mutating the sequence. So imagine that you still want to do a mutation, like I want to make this residue a bit shorter, but I want to get rid of part of the chain, I don't know, or something like that, something that is more similar. Maybe but you still want to keep the conformation. Maybe you just want to get rid of the extra atoms, okay? Imagine that you have a phosphotyrosine. Now you want just a tyrosine without the phosphide. If you get rid of everything, okay, it will reconstruct a new tyrosine, which can be in a completely different conformation, okay? Because it's reconstructed.
Yeah.
But so instead of it, you just get rid of the phosphate part and keep the rest, okay? Just giving you an example of things that can. So this mutated residue is something quick and dirty to just get
this all has to happen before
the building. Yeah. So this is on the preparation to that you'll see in the next talk actually. Okay, the building process.
Other question? Okay, then coffee break.